Hi everyone, really nice to meet you all, and thank you so much to the organizers of this event. We're really grateful. Chloe, Ivar, and I are really grateful to be able to speak about our work here. And today we'll be presenting on wetware computing. We're really sorry for not being able to make it in person today, but we're so grateful and happy for the opportunity to be a part of this discussion. This is a work in progress presentation, which means that we'll save a lot of time for questions. And we'd love to hear everyone's feedback on these ideas later as well. So just to start off, I'm going to introduce myself. My name is Jenn. I work as a lecturer at University of the Arts London, and I'm a creative technologist with a game engine kind of like specialization.
Hello everybody, I'm Ivar. I currently work as an AI engineer and also studied philosophy.
Hi, everybody. My name is Chloe. I work in AI ethics and bioethics out of Canada. And thank you so much for letting us record remotely today.
So just to start off, we'll be starting with some framing and we'll get into our core ideas on morphing ontology, and we'll be using organoids specifically as an example today to talk about how we can develop multi-scalar coevolution with wetware computing. So we think just to start off, we're going to introduce the idea of wetware computing as a form of non-anthropocentric intelligence emerging. So currently, wetware computing is emerging as a new computing paradigm that's alternative to artificial neural networks. In this paradigm, computation tasks are performed via synthetic biological matter, such as what we'll be talking about today, organoids. And in this talk, we'll be arguing that integrating wetware computing into scientific knowledge production can allow us to find a non-anthropocentric form of science, one in which the relationship between subject and object becomes discursive rather than unidirectional.
Yeah, so we can argue that in a certain way the current scientific feedback loop of knowledge production is anthropocentric in the sense that science has often been guarded by the myth of objectivity, and this notion of objectivity is often centered around the human perceptions, tools, skills, categories we use to make sense of the world. And as a consequence, what that means is that what we understand by intelligence defines how we're seeing new forms of intelligence, and that this is then determined by a human notion of intelligence. So it's in a certain sense a static loop in which we are closed right now. And this is a point which is also made by Yukui in his book Recursivity and Contingency, in which he basically says that contemporary AI and AI development is dependent on a logic of recursively incorporating contingencies, meaning that by this like it's guided by this myth of objectivity to make the whole world rational, rationalize everything by means of predicting it. So every contingent event is being consumed by this predictive logic. And then as a consequence, this has also the effect that AI can be seen as an ontological problem because the development of knowledge according to the singular logic entails the homogenization of thinking, in which non-human ways of knowing are excluded, which we see, for example, in the work of Christina Liu and Matteo Pasquinelli, when they talk about that AI is like this flattening of culture and knowledge because it just approximates the mean. And so it just perpetuates anthropocentric human categories, predefined human categories. And part of the reason why this is the case is because AI hardware can in itself be said to be anthropocentric, because AI models often run on silicon-based hardware and they contain a central processing unit, a CPU, meaning that information is processed top-down, but also the architecture itself is static. So the architecture of the model itself is static because which layers it has, how many layers it has, that is all predetermined by humans and it cannot be dynamically updated. So Yeah, then the question arises, how can we grow adaptive hardware which can enable models which can adapt themselves better and arguably are less anthropocentric? So this is basically the question, how do we go from a static ontology to a morphing ontology in which we do not assume predeterministic forms of knowledge, but rather adaptive categories which are materially and relationally embedded, and a reorientation which demands that we rethink what counts as intelligence, agency, and even thinking. We could say that such a framework resonates with new materialist insights, which posit that matter itself participates in meaning making.
And just like I said at the beginning of the talk, we think there's a potential solution to be found in hybridized artificial or synthetic biologies to help us move away from this anthropocentric paradigm and shift towards non-traditional forms of computing to help with this knowledge production. We think that moving towards non-traditional deep learning, for example, some forms of reservoir computing or OI may allow us to move away from this subject-object paradigm and to move towards a more relational understanding of what knowledge production could look like. And we think this also helps understand knowledge upon multiple scales. Would you mind moving to the next slide, please, Jen? So my work at Cambridge was on the ethics of organoid intelligence. I'll get more into what organoid intelligence is specifically, but we use this as a case study example to move towards potential substrate-dependent forms of cognition. So OI itself realistically offers an alternative to the predetermined ways of knowledge production. It might be said to be predeterministic in the sense that organoid neural assemblages are set to mimic human neural network architectures, but OI itself has the same neuroplasticity that human brains do. That makes it adaptive, and unlike silicon computing, its architecture is not fixed. So this matter is not a passive object of knowledge construction, but an active co-constructor of knowledge production. And here's a little bit more about cerebral organoids themselves. So they could be referred to as cerebral organoids or human brain organoids. They are three-dimensional structures grown from human pluripotent stem cells, and they mimic aspects of the architecture of the human brain and the functionality of the human brain. They are not shrunken down versions of full human brains, but they do mimic models of sections of human neural architecture. And they are encultured in environments that promote self-organization into these structures that resemble these regions of human brains. Here you can see an image of the brains being cultured in a petri dish, and HBOs are traditionally utilized to study human brain development for modeling neurological diseases, drug testing, and assessing neurodevelopmental processes. And despite these simplified structures, HBOs exhibit neural activity such as delta brainwaves. We'll get back to that in a minute, but the most tangible part here is the shift towards organoid intelligence. So by interfacing these cerebral organoids themselves with a high-density multi-electrode array, you get something called organoid intelligence, which are cerebral organoids themselves that are connected to the web or to a form of artificial intelligence. So brain organoids themselves are mounted onto these multi-electrode arrays, which means they receive electrical inputs and send out electrical inputs. They function similar to how human brain-machine interfaces exist. Organoid neural networks process spatiotemporal electrical signals and respond to these stimuli, demonstrating learning through adaptive neuroplasticity. This creates a bidirectional communication system between the human brain organoids and the AI systems through the multi-electrode arrays. And I guess next slide as well shows the neural activity of these brain organoids. So it is set to be improving. This is still pretty early proof of concept of this technology, but human brain organoids register currently delta brain waves, which is the same as premature infants in humans. And a couple prominent examples of the organoids themselves is this dish brain experiment, which demonstrates how human brain organoids can be integrated into simulated game environments such as Pong. The primary objective of this dish brain experiment was to explore the capabilities of human brain organoids to perform goal-oriented tasks when provided with sensory input and feedback. So the dish brain grew on the high-density multi-electrode array. And this is the recording of its simulated electrical activity. It involves grid electrodes that deliver electrical stimuli to specific regions of the neural network. So specifically here for the Pong environment, the way it works is the virtual paddle, if it was successful in hitting the ball, the positive feedback signal was sent to that sensory region to reinforce this behavior in the brain organoid. And if the paddle misses the ball, then a negative, less predictable feedback signal was sent to the neural organoid. And this is, I think, the last example we're showing today, but currently on the Final Spark website, which is the primary business model for organoid intelligence currently, you can go play with their interactive butterfly demo, in which the human brain organoids control this virtual butterfly in a simulated environment. However, it is worth noting that there's been some speculation that these organoids, if they are to ever be deemed conscious of their surrounding environments or have some form of feeling or sensory perception, then that these organoids would be deemed virtually embodied by the butterfly. It is like the organoids themselves believe they are the butterfly, which is very matrix coded. So, and Jenn?
I think to be able to traverse towards the age of wetware computing, we also have to get through two things. So we have to understand how our tools can now learn themselves in their own morphing fluid without a predetermined architecture. This also demands us to shift away from the subject or object paradigm that frames our current understanding of knowledge production, where we need to bring two things into kind of the spotlight, one being understanding the wide scales of contingency. So this is in response to Benjamin Bratton and Yuk Ho. Secondly, we also have to understand through those organoid experiments that and examples that you've seen, the varying scales of agency. So first, understanding the wide scales of contingency, just wanted to revisit this quote by Benjamin Bratton in The 5 Stages of AI Grief. He explains how, like all complex technologies, AI is built of many simpler previous technologies, and a lot of them are contingent. And these decisions of convenience are reinforced through positive feedback, which they become stacks. So chances on rails, it all comes together at a point where its extreme contingency becomes unavoidable. And in response to the concept of contingency in the world of wetware computing, we also wanted to see how scales work in relation to wetware computing and how scales scaffold for organoid intelligence. So this is a polycomputational framework we've designed in a paper. We've designed for a paper that was published in an MIT digital journal recently, and the paper is called Organoid Array Computing, the Design Space of Organoid Intelligence, where we looked at the scales of wetware computing and how even at the level of chemical computation, there's already agency involved. That's in response to Laura Tripaldi's Parallel Minds and also Michael Levin. We also want to respond to this paper by Josh Bongard and Michael Levin that says how biological systems are evolved, overloaded, multi-scale machines. And we feel that this is a really, really important and useful take for us when we're considering wetware computing seriously. It also kind of points us to our next kind of speculative framework, where we wanted to look at the potential for organoids to optimize for specialized learning and multimodality. This means to expand types of inputs to receive multimodal capabilities. And if this could be achieved, the organoid neural network array is sophisticated enough to process these inputs as well, because it has extremely strong computational power. And in some existing research, we can already see how human brain organoids are used for speech recognition. So it can identify vowels. There's also a long list of really successful and interesting experiments that's attempting for organoids to understand multimodality. It's also worth noting here that there are so many different types of organoids, so not just cerebral organoids, but also some that filter toxins like kidney and livers, and they have a type of organoid that's also designed to process smells. And in the future, we also speculate that there will be so currently assembloids are used for a lot of medical research, which is combining different organoids. And assembling them basically. We also speculate that this process will potentially help us further computational power. And with that, at the final output layer, there's a type of ECG output recording that's currently processed by linear regression models, which will also very likely become more advanced in the future. And so therefore, we really think that Wetware computing could be a really important and almost necessary step for us to rethink human technology relations, in that it enables us to rethink structures of adaptivity and interscalar agency. We think that this gives us a new age of computing that has a non-anthropocentric character. It also opens up a new way for less anthropocentric AI models. So yeah, thank you very much for listening. This is just a very quick work in progress presentation with lots of gaps to fill in as we write it into a paper. And again, we're really sorry we couldn't be here in person. We're scattered across 3 countries right now, across different time zones, but we would really welcome all types of feedback, comments, questions, and concerns. Yeah, thank you so much. And feel free to scan the QR codes and get in touch. But yeah, let's open up the floor for questions.